Indu, over to you. You have the floor, and I will let you know if there is any burning question that I have to interrupt you. I will. Otherwise, we will wait until we will finalize your presentation. So the floor is yours.
Thank you, Tilina. First of all, I want to thank everyone who is attending this talk, and thanks Europlanet, Tilina, everyone to invite me to actually talk about MERTIS to school students. And I think it's a very, I know it's a very interesting project on board BP Colombo. And it's gonna tell more about Mercury surface and how it evolved and how Mercury volcanism evolved and everything. So let's see more little bit about Mercury. If you see, apart from Earth is the only planet, Earth and Mercury are the only planets in the inner solar system with its own magnetic field. So Earth and Mercury has its liquid core, and that actually has its own magnetic field. If you see Venus and Mars, they do not have magnetic field. Why Earth and Mercury alone got its own magnetic field? If you see Mercury, it is a very small planet, means it is supposed to cool very soon. Irrespective of that, Mercury still has its own liquid inner core, and that's a very important question to answer. Why? If you compare the planet radius and core radius, Earth radius itself is like 6,300, 400 kilometer, whereas the core is just 3,400 kilometer. If you see Mercury, the entire planet radius is only like 2,440 kilometer, means we can actually fit Mercury inside Earth's core, whereas the core radius of Mercury is 1,900 kilometer. Means almost the entire planet, it's just the core. The rest 500 kilometer is what the mantle and the crust is. So why Mercury happened to be such a planet with a very dense core? It's one of the very important question to answer, and we still do not know what exactly the reason. One of the very interesting hypothesis or theory is that there was a giant impact on Mercury. Mercury was once like a planet with a proper core radius, mantle to crust radius like Earth, but however a giant impact impacted on Mercury crust, which has blown away most of the planetary upper crust, and this is what we left out with. But these are the hypotheses and theories that still yet to be tested with proper evidence, and that's why we need more missions, more efficient missions like Baby Colombo to Mercury. So if you see like a very early days, like very long ago, this is how Mercury, how we saw in the night sky. It's a very small dot in the night sky. But once we get to have some common telescopes, the picture of Mercury starts to expand. So in 1889, this is how Schiaparelli saw Mercury could be. At 1934, Antoniadi came up with more details with some more names than Schiaparelli. But this is the first ever close view of Mercury we ever got in 1975 by Mariner mission. One of the very interesting fact of Baby Colombo, how Baby Colombo itself got name is, during the Mariner mission, it was a NASA's mission. It was the first mission which went very close to Mercury, and the Italian astronomer scientist called Giuseppe Baby Colombo. So he is the one actually came up with a gravity assist, in which we not only can see Mercury at once, we can actually see Mercury to more than 3 flybys using a gravity assist method. And that's why we actually named our European space mission to Mercury as Baby Colombo. So there is this interlink between Mariner and Baby Colombo mission. But this is the first ever full view of Mercury that we got from the NASA's Messenger mission. It is the first orbiter to mission. Mariner did not orbit Mercury. It had 3 flybys. It just went close to the Mercury, but couldn't orbit the Mercury. But by 2011, we could orbit the Mercury, and we could get an entire picture how Mercury is in real. And this is very colorful image, and what different color says is different composition or chemical environment of Mercury. And I will just show what more Messenger told us how Mercury surface really is. If you see the picture in the left, It shows very bright red craters. In the right, you can see these ringed basins on Mercury. Here you can see the basin after this crater formation. There is actually a not plate really, but tectonic events on the Mercury. Here you can see a very nice pyroclastic flows. And so Mercury very close to the planet. Why it should contain a volatile enriched interior? If a planet forms very close to sun, we do not expect it to have volatiles trapped into its interior. We expect it to escape due to the surface, due to the sun's activity. But then Mercury holds lots of volatile in its interior. This is one of the pyroclastic flows. If you see, you can clearly see like a lava flow which is dividing, which is eroding the other intricate planes and flowing through the different basins. Here you can see a very light material from a very collapsed pit. When something is very light material is actually escaping from the surface, or something like a exposed from the surface, and what are these materials are, it's still a clue. And you also see such a beautiful pattern ground on Mercury due to tidal and contraction of Mercury. You can clearly see there are some ridges and there are some contractions. And one of the most interesting and very unique feature of Mercury are these pits. These are called, we call it as hollows on Mercury. Something, a very volatile rich Mercury, volatile rich material came to the Mercury surface, and it just escaped from the surface due to sun's activity, means including the surface temperature of the Mercury, and also due to other photoionic radiations from the sun. And what are these materials are, and you see these type of surface features throughout the Mercury. And in the talk, I'll focus more on this feature on Mercury. So little more about Messenger. So Messenger is the first orbiter to Mercury, and it has got us lots and lots of data. And one of the most interesting thing Messenger told us about is how Mercury is more mysterious than we previously thought. Messenger was aimed to actually give us more clues, more understanding about Mercury, but though it answered many questions, it brought us more important questions that forced us to actually make a better and more efficient planetary mission like Bepi-Colombo to actually many more important questions. If you see the Messenger orbit, it only could actually image the northern part of the Mercury, because Mercury is very hot, it is very close to the sun, and we cannot really revolve, we could not, at that time, we could not really come up with a mission which could orbit very close to Mercury and have a very global picture. So what Messenger did, it had a very long elliptical orbit, in which during its northern hemisphere it was closest to the Mercury, and around its second hemisphere it was very away from the Mercury. So most of the things what we actually saw from Mercury, all those beautiful pictures, is actually from the northern part of the northern hemisphere of the Mercury. So we still have to explore more of the southern hemisphere of the Mercury, and again that's where Bepi-Colombo comes into picture. Like I said, not only Messenger told us that Mercury is different and very unique, it also showed how different it is actually from Moon. Before Messenger, we always thought, okay, Mercury is more closer in resemblance to Moon, so we expected like minerals more closely in resemblance to Moon. So if you see Moon and Mercury, they are almost same surface features, all cratered surface with little darker materials on the surface. But when we put the mineral map of the Moon and Mercury, though they have very colorful pictures, these colors from the Moon are actually brought from different minerals than Mercury. How we can say? From spectroscopy. If you see the spectra of the Moon, like in the visible IR, visible infrared region of the spectra from the lunar minerals actually have very good band features, and these bands are actually due to very high iron and titanium content in the minerals. So if you have a mineral with more iron. So iron is a key player in actually creating these band spectral features. If we have iron in a mineral, they actually make these beautiful bands in the visible infrared. But if you have a mineral, or if you have a surface with no iron, you do not see those bands. So that's what happened when Messenger gave us visible infrared data of mercury. If you see the left hand side, all the data, they have no bands. If you have bands, then you can say what mineral they are. If you do not have any spectral features, it is impossible to predict what exactly the surface is made up of. And that's why we not only need visible IR, we also have to need a different spectral region where we can understand mineralogy of the mercury. And that's where MERTIS comes into play. So MERTIS is a thermal infrared region where the spectral region is from 7 to 14 micron, where it doesn't depend on what cation it's there. I mean, what is it an iron or is it something? It doesn't depend on that. It depends on the molecular vibrations among the mineral itself, and it mostly related with the silica abundance of the surface. If you have more silica and oxygen bands, more the bands, the more different the spectral signatures are at the thermal infrared. So here, just a quick clue into BepiColombo. I'm sure everybody had got lots of cues from BepiColombo. So BepiColombo is a twin satellite mission. I think it is the first 2-orbiter mission to any planet. So one orbiter is from ESA, which is a Mercury Planetary Orbiter. So here is ESA's Mercury Planetary Orbiter, which will, if you see the orbit of the Mercury Planetary Orbiter, it is very close and almost circular when compared to the Messenger Orbiter, where it was more elliptical. And this is JAXA's Mercury Magnetospheric Orbiter. And these two orbiters combine together to tell more about Mercury's surface, its magnetosphere, and its plasma environment. The planetary orbiter focuses more about the planet itself, how it's formed, how it's evolved, and why its surface features happen to be they are. And whereas the Mercury Magnetospheric Orbiter focuses on what is the plasma environment on Mercury and what the magnetosphere of the Mercury is. So it more studies the atmosphere and the environment around the Mercury itself. So this is like the actual stack of BepiColombo. This is the transfer module, which actually takes both the orbiters to the Mercury surface. So this is the planetary orbiter, and all these white, these are the multi-layer inclusions, which actually protects the orbiters from the sun's radiation as it goes closer to the sun. And here, so this is a sun shield inside which we have the magnetospheric orbiter. So you might have seen very beautiful launch videos of BepiColombo. This video is actually taken by Jan Halbert. He's my advisor and also the PA of the MERTIS payload in BepiColombo. So I thought, in case you would have missed this, this is the thermal camera view of the BepiColombo launch. So as I told, MERTIS is a thermal infrared imaging spectrometer. So this is thermal video of BepiColombo itself. You can see how hot the launcher itself. So enjoy the video. Thank you. And so this, I know it's a very boring picture. You must have seen all those beautiful flybys that BepiColombo does before it reaches to Mercury. And why do we actually have to do such a complicated orbit to reach Mercury? It's because as we are moving closer to the sun, BepiColombo is constantly getting accelerated and at such a high speed that we cannot control we cannot control in an instant. If we have to control that, means we need to bring lots and lots of fuel, and that is not a very wise idea. So if you see the propulsion, it is electrical propulsion. So more like how astronauts do spacewalk. So then they have these small thrusters in which they maneuver themselves, and it's kind of way how the BepiColombo itself maneuvers itself and changes its orbits as it goes close to the sun. So it needs Earth flybys, it needs all these Venus flybys to actually slow down the spacecraft as it moves very close to Mercury. And actually there are beautiful videos from ESA on these flybys. Here is one of the link in which I'll share it later for you can see. So this is where MPO and MMO will be as it reaches Mercury, which is very different from how Messenger actually viewed Mercury. So Bepi-Colombo will actually have a more circular orbit which studies the planet, so that we can get the global view of the entire planet. Here is a very small video in which you can see it's not that these orbiters are orbiting the planet, they are orbiting in a very sensitive, sensitive sun atmosphere. All these cyan lines, they are the magnetic field, and here is the sun. You can see the sunlight, and you can see how nicely MMO is actually studying from all the magnetosphere and the plasma environment of the Mercury. And you can nicely see how as the planet rotates, MPO also studies takes the whole global picture of the Mercury. So we know both about the northern and the southern hemisphere of the Mercury from Bepi-Colombo, and through very varieties of instruments. So so this is MPO. MPO has like 11 instrument suites, and one of the instrument suites is MERTIS. So MERTIS is a mercury radiometer and thermal infrared imaging spectrometer. Means MERTIS as an instrument itself is a dual instrument suite. It has two instruments inside. One is spectrometer, imaging spectrometer, which images the mercury surface from 7 to 14 micron. And it also is a radiometer, means it not only takes the spectra, it also measures at what temperature of the mercury surface the spectra is taken. And this is the first ever orbiter to Mercury, which is capable of measuring the actual surface temperature of the Mercury and the behavior of minerals at that surface temperature of Mercury at 7 to 14 micron. And this is MERTIS itself in collaboration between DLR and University of Munster. And this is this is the flight model of MERTIS, and here we have Jan Helbert seeing the actual flight model of MERTIS, which was integrated at 2013 to Bepi-Colombo itself. And if you see the interior of the lens, I mean the pipe of the MERTIS, you can see such a very high reflecting surface. And what this high reflecting surface does is, though we are at a very higher orbit, because of the mercury surface temperature, in the baffle, the surface temperature will be actually 100 degrees Celsius. You do not need 100 degrees Celsius actually reaching your electronics, and that is not good for the instrument. And what this surface does, it reflects all the light, all the radiation that reaches MERTIS. So at whatever the temperature, MERTIS will be always cooler than 30 degrees Celsius. And MERTIS, that will be always be very efficient in actually mapping the surface mineralogy and the temperature of Mercury. So the main scientific goals of MERTIS is we want to map the global surface mineralogy of the Mercury at 0.5 kilometer per pixel. So 500 meter per pixel, we want to study what the minerals on the Mercury is made up of. What are those hollows made up of? What minerals actually make up these hollows? And what is the volcanism of Mercury made up of? And when did this volcanism come to the surface? And is there any changes in volcanic material to the Mercury surface with respect to its age? And all these answers will be actually told by MERTIS. It will also say how cold the Mercury poles are and how hot the hottest part of the Mercury surface are. And these are the clues. We have to wait up to 2025 for MERTIS to answer about Mercury. So this is the This is the MERTIS when it was integrated in the spacecraft at October 2013. And is it enough? Is it just enough to have an instrument on board Baby Colombo? And is it enough just to have the instrument on a mission? No, we also have to understand how the minerals, how different minerals that we could expect on Mercury actually behave in that surface temperature under vacuum. For that, we need a laboratory facility where we can simulate Mercury surface temperatures on Earth, and we can bring different minerals, different Mercury analogs, and study them at that temperature to know how MERTIS will actually give a picture about Mercury. So I'll do it in a little bit more detail. If you see, these two are the different spectrometers in PSL's Planetary Spectroscopy Laboratory at DLR Berlin. And here, I hope you can see the arrow. So this is the simulation chamber, and this is the chamber where we actually create planetary surface conditions. And here we simulate Mercury and Venus surface conditions. And both the instruments together, we can not only study the thermal emissivity of the minerals, but we can also study from ultraviolet to far infrared spectra of both fresh and the thermally processed minerals. So we can do reflectance, transmittance, and emissivity at kind of all wavelengths. And we can also study, we can also simulate surface temperature and surface conditions of Mars, Moon, asteroids, comets, and of course Mercury and Venus. And what we do basically in the lab, so we take different Mercury analogs or any planetary analogs. And in this talk, I'll just focus on Mercury right now, in focus to Baby Colombo and Messenger. So we take Mercury analogs, we keep it in inside the planetary chamber, like the pictures you see in the right side of the slide. So you keep the sample cup. In sample cup, you keep a very powdered material. Why very powdered material? Mercury surface, it is very regolith rich surface. What regolith is, so if you see the first steps by astronaut on Moon, the first footprint actually shows how fine particles the Moon surface is, and Mercury surface has a much more thicker deposits, thicker productions of those particles, because the comets and the asteroids which constantly hit Mercury surfaces, they travel at a speed of 45 kilometers per second, and it produces very thicker, very fine particle regolith on the Mercury surface. So most of our analogs are actually very finely grained powders. So we take different powders and we slowly heat them from room temperature to Mercury temperature, which is 500 degrees Celsius. And as we heat them, we measure the emissivity spectra of the mineral and under vacuum. So that's what happens in Mercury, right? So in Mercury, after the day slowly comes up. Mercury itself is more of vacuum, so there is no, it's vacuum, and we slowly, the surface heats to 500 degrees Celsius for like 83 days. And that's what we do in the lab. We slowly heat the minerals to a very high surface temperature, and we also take spectra at those temperatures. So we not only have spectra from the start and the end product, we also can see how the spectra evolves with the increase in temperature. And after the measurements, what we do, we take both the fresh analogs and also the thermally processed analogs, the heated analogs, and study how the reflectance behavior of the analogs changed from the fresh to heated minerals. And using this, we create a very specialized spectral library for Mercury. So if you want to understand Mercury, if you want to understand surface minerals of the Mercury, we need to have such spectral library in which the spectra was actually taken under Mercury conditions. And those are the spectral library which will be help us to actually learn what Mercury surface is. So we saw before these hollows on Mercury, and how these hollows are actually formed. until now, the only spectral evidence for the hollows is to form is via sulfides. So among messenger data, we went through these craters in which we have these brighter hollows, and we take the spectra of these hollows. They had a they had a strong spectral absorption feature around 600 micron. If you see the normal Mercury surface, which is at the bottom of the bottom of the graph, it has no spectral feature, but inside these hollows they have these spectral features. But what are these spectral features are made up of? When we compared the spectra of sulfides taken at the PSL laboratory, we could see that these hollows actually matches with the magnesium and calcium sulfides. So okay, if sulfides are the products of these hollows, and how that hollows actually came to the picture. And this is from Helbert et al., Jan Helbert et al. 2013. So there were pockets of volatiles, including sulfur, which is reaching Mercury surface. And when it comes to the Mercury surface, it comes to the surface in the form of slags. And due to very high surface temperature, because it's volatile, and we are exposing volatile to like more than 400 degrees Celsius to the surface. And due to this very high surface temperature, these volatiles get decomposed and leaving us with pits. Because it decomposes, it escapes to the atmosphere of the Mercury, and we are left with these hollows. Here's very one nice example. So when we were studying different sulfides behaving under Mercury conditions, this is an example of magnesium sulfide for 1 Mercury day. So what we did, we kept magnesium sulfide, pure synthetic magnesium sulfide in the sample cup, and we slowly heated magnesium sulfide for 1 Mercury day. And you can see, and this is 4 hours of experiment. I have just fast forwarded to 1 minute. You can clearly see the sulfur being deposited in the mirror, and the sulfur being deposited around the sample cup means the magnesium sulfide itself is decomposing into magnesium and sulfur, and that's what we see here. And we still haven't reached Mercury surface temperature. And you can see how, now you can see this explosive behavior, just material itself is thrown, and we still haven't reached Mercury surface temperature. See, can you see the bottom of the sample cup? And this is what happening on Mercury. So when magnesium sulfide comes to the surface in the form of slag, due to just surface temperature, this is not external temperature, this is just normal Mercury day. In a normal Mercury day, there is a slag on Mercury surface which is made up of magnesium sulfides, and in 1 Mercury day, magnesium sulfide can decompose and escape, and you can see all the sulfur deposits throughout the sample chamber. See, and that's what we think, that's what this hollow should be made up of. If you see along the arrows, you can see the materials being deposited, something very similar to what we see in the lab. And this is what we do in the lab. So we take different analogs, we take different minerals and test them under Mercury conditions. We not only study the mineralogy, composition and spectral behavior of the samples, but we also study the surface morphology of how at very high temperatures, how a morphology of the sample itself could differ, and how the sample itself could have a different behavior. So if you see these hollows, all the black dots on this map is all such hollow features. And these hollow features are everywhere on the surface of the Mercury. And we cannot say that it's only magnesium sulfide is the only nature of these hollows without actually understanding what is the mineralogy of this hollow. So it is very important that we need to take very different sulfides, and also test them in a Mercury conditions, and also mixtures of sulfides, and also test them in Mercury conditions to understand the formation and the evolution of these hollows. So that's what we do. We take different sulfides like manganese sulfide, iron sulfide, chromium sulfide, titanium sulfide, and we take these sulfides and we slowly heat to the mercury surface temperature, and we take spectra at each temperature. So you can see that the spectra itself evolve at different temperature. And here again we have sodium sulfides, calcium sulfide, and 2 magnesium sulfides. So if you see the sodium sulfide, if you compare the black and the red spectra, you can clearly see how different the spectra itself at different temperatures. So what does this say? We cannot simply take a spectra at room temperature or a very low temperature of a mineral and compare it with the actual spectra taken from the mercury surface. So this is why we need a specialized lab in which we should create specialized spectral library in which the spectra was taken under specialized planetary conditions. And this is very important, and these examples of different minerals actually show why we need to have such a laboratory facility to actually study the different planets like a Mercury. If you see calcium sulfide did not really show much differences in the spectral behavior for one mercury day. But what we did, we tried to reheat the same calcium sulfide for different mercury days, and voila! At day 2, by the end of second mercury day, calcium sulfide also evolves to a different spectra. So that's how important we need to understand how just the surface temperature on mercury can actually change the composition, the chemistry of the minerals on the mercury, on the surface itself. So this is after all these measurements, what we did, like I said earlier, we take it to the reflectance chambers, and we take reflectance from ultraviolet from 0.3 to like 100 micron, like very far infrared, and you can clearly see among different wavelength range, the thermal infrared is the only wavelength range we can actually differentiate between different sulfides. Though in the visible infrared and in the UV, though we may able to say, okay, whether there's a sulfide or not, the thermal infrared region, the Mertis region is the region where we can not only say we have sulfides, but we can also say what type of sulfides are actually on the surface. And that's why Mertis will be more powerful to not only understand the mineralogy of hollows, but also understand what are the hotspots of the hollows. I mean, on what depth these slags came from, and what is the chemistry of these slags, and all these things will be answered by a Mertis. So if we take any planetary missions, it is not just that we take spectra, it also depends on what phase angle. What is a phase angle? It's just the angle between the sun and the orbiter. So the angle between the sun and the instrument at which it sees the Mercury surface. So the more nominal is to have a very low phase angles, but missions like Messenger, it has a very wide phase angle, means it actually took the surface mineralogy or the spectra at like 80 degree. So the angle between the sun and the instrument was like 80 degree with respect to the surface. And so it is also important to understand not only the reflectance, but also the behavior of the reflectance spectra with respect to different phase angles. And this is one of the examples from UV to far infrared for the manganese sulfate. You can clearly see around this region that different phase angles actually impacts the absorption depth of the spectral features in this region. So that's one more thing that PSL is capable of doing it. And this is just another view. Here until now we talked about sulfides, which are volatiles, which can actually form these hollows. But what about the actual surface mineralogy of mercury? That which we still do not know. So we still do not know what's actual surface mineralogy of mercury. What is the actual silicate? Is it basaltic rock, like like Hawaiian volcanism, or what type of rock is actually surface made up of. So if you see in the Mertis, different rocks actually have different spectral behavior, and that's what we need. So we need distinct spectra to actually differentiate between the different minerals. And especially for mercury, where we do not have any iron to, or enough iron to actually have spectral features in visible infrared, we need Mertis to actually know about what's the surface mineralogy of mercury. So, but do we have to really wait up to, up to Mertis to reach mercury, which will be 2025? We do have some data collected at this spectral range, which is the mid-infrared. So if you see the observations are from like 1988 till now, there are very few observations in which astronomers use different telescope facilities and try to understand mercury at this spectral range. If you see the spectra taken using these telescopes, they are very noisy, and we do not know how good the spectra was calibrated for its atmosphere and all other calibrations. We cannot depend on that, but this is the only information available about mercury under this spectral range. So what we can do up to when Mertis reaches mercury is to understand what this spectra is actually made up of, and that's where we use spectra library taken from PSL and compare it with the actual mercury spectra. And if you see the left hand side of this slide, you can see different color boxes. So means each spectra actually taken from a very wide range, very wide surface range, like we can say like 50 kilometer by 50 kilometer, and much more than that. We can say 100 and 500 kilometers. So each spectra actually can say 500 kilometer per 500 kilometer. So in 500 kilometer by 500 kilometer on Earth, you can see all varieties of things, from buildings to lakes to trees. But in mercury, of course, we do not have such a variety as we see on Earth, but then we do have volcanic activities, we do have mixtures of other surface materials, we do have craters which is excavating interior material to coming outside of the face. So what we have to do, so we have to unmix this spectra to its own mineral components. That is one more thing we do at PSL, is that we use machine learning and AI techniques, artificial intelligence techniques, to actually study what these spectra are actually made up of. Apart from this, the one more thing what we are recently trying to attempt is this study. So this study came last January, and this study talks about silicate mineralogy at the surface of mercury. So I told you earlier that we still do not know about the silicate mineralogy of mercury, but how this study is trying to interpret the silicate mineralogy of mercury. What they do, they take the powders of different oxides of each geochemical regions of mercury. So the different colors on this slide tells different chemistry of the surface, and this information is taken from the gamma ray spectrometer, neutron spectrometer and an X-ray spectrometer of MESSENGER mission. And if you see the southern part of the hemisphere, we still do not know, and we call it as integrated terrain, and different colors actually say different composition. And what this study did, they took the composition of the different terrains in a small cylindrical tube, and they melted those powders to like 1200 degrees Celsius, and they slowly crystallized, they slowly cooled down the melt to form minerals. And once they form the minerals, once it solidifies, means to see what is the actual mineralogy of the surface. So if you see, so these are their samples. They are like 5 mm by 5 mm, and each 5 mm by 5 mm represents such a bigger terrain on mercury surface. And thanks to Olivier Namur and Charlier, they gave us those samples. And what we tried to do is with PSL and with other collaborators to actually take the spectra of these samples and see how we can actually understand mercury through MERTIS and other instruments regarding the surface mineralogy of the mercury. So these samples is the closest to what we have with the surface, with the silicate mineralogy of mercury surface itself. So here you see, this is the bidirectional reflectance suit of the spectrometer of the Bruker instrument and the PSL, and here you can see the samples. So luckily, the minimum aperture we can do is like 0.25 millimeter, and as the sample size was like 5 millimeter per square, we could actually sit on the sample, and what we got, voila. So we can clearly see, so all these different names, what I have in the slides, these are different geochemical terrains on mercury. And what we have to know from this slide is that different geochemical terrains have different spectral behavior. And of course, we still have to wait for MERTIS to reach mercury to actually see, okay, how close we are to, we were actually to understand mercury using such experiments. And we will also use this spectra to compare with the telescope spectra what we saw earlier, to actually see, okay, what the telescope spectra was actually made up of, and how close we are to and understanding the silicate mineralogy of the mercury surface. So one thing what we attempted is, I told you, like we saw earlier, that these samples are 5 mm by 5 mm, and each 5 mm by 5 mm has different minerals. They have more than like 3 minerals, and we do not know where the minerals are, and it is important to know what is the spectra of those minerals within the 5 mm by 5 mm square meter sample. So what we did, we took the scattering electron microscope of the sample. Means in simple case, we did elemental mapping of the sample using the facility from Naturkunde Museum in Berlin. And you can, this is one of my favorite picture, because we have this heart shaped, mineral in the sample, and we hope we have such more heart shaped minerals on mercury surface itself. And what we did, we took the elemental composition of this sample, and we aimed to take the spectra of each mineral within the sample. Means we have to go down to nanometer scale. We have to take spectra of each point in the sample under nanometer scale. So that's where we collaborated with the BESI. So this is a synchrotron in Berlin, which sits like very close to the DLR itself. In the synchrotron, we have this very high synchronized beam, the light beam, so that we can focus, because they are very highly focused light beam, we can actually focus the light beam to sit in the nano scale on the samples. So this is one of the example. So if you see the sample, like we can actually sit on those pink spots, we can carefully make the light sit on those pink spots and measure the reflected light for those pink spots from 7 to 14 micron. So of course this will be a reflectance, but here we do 1 minute reflectance, which is little bit closer to the emissivity spectra. And in this way, we can not only study what is the bulk mineralogy, like what we studied in PSL, but we can also see what each mineral end member in the sample spectra actually is. So this is how we try to understand what we can do, what we can understand mercury through MERTIS. So this is what preparation study is. So we have a lab where we can build the spectral library, and we keep building different bigger spectral library for the upcoming years until we reach mercury. And we prepare and we try to understand this using this spectral library, what the ground-based telescope observations at MERTIS spectral range tells us, and what different analogs like these experimental products, how we can use these products to understand mercury at the MERTIS spectral range. And we also do some of the we try to attempt some of the automated spectral analysis or spectral characterization techniques. So it is not that Mertis will give the data. So as Mertis gives the data, how fast we can actually get to what mineral the mercury surface is. So instead of manually downloading, instead of manually taking each data and search for its mineral N numbers, we are attempting to do automated mineral classification as we receive every new Mertis data.
Indu,
You.
no, sorry, go ahead.
So this, I thank you for patiently listening about Mertis, listening about Bepicolombo and PSL, and how we incorporate PSL and Mertis to actually understand mercury from Bepicolombo. And these are the different Twitter links for you to follow. So PSL Berlin is if you want to want to know new updates about PSL Berlin, and Mertis on Bepi, it's to know updates about Mertis, Bepicolombo. And here also I have email ID if you have any other questions in the study, what I do or what we do. In the top here you have the team. So this is the PSL and Mertis team at DLR. And so Jan Halbert is the PA of the Mertis with the Mertis instrument itself. On the rightmost corner, we have Alessandro Martellini, who is the lab manager of PSL. And we have Mario next to me, who is our machine learning expert. And he is the one who is actually writing the Mertis pipeline. So he is converting the telemetry data to the raw data and then to calibrated data and usable data so that scientists can use the data and study what mercury is. Thank you.
Thank you very much, Indu. That was a very comprehensive talk. I think we do have to go back and listen to many of the things that you said. There are so many new information. I actually didn't know we could do so in-depth analysis of everything that we are about to find yet in Mercury. So that it seems we're going to have very exciting years ahead while we wait for Bepicolombo to reach Mercury in 7 years from now. We don't have much time, but I will try to share a few of the questions. I think, Steph, we have a video with a question for Indu. Do you want to play the video now, or we continue with the random questions?
Okay.
Steph, are you there?
Yes,
Steph?
I'm here. Yeah.
So,
Oh, hang on a sec.
can you launch the video? How do we do that? I don't know how to do that. So we have a question for you that was sent via YouTube video. So
Okay.
I don't know if I just share the link here or if Steph is going to do it. No, maybe, okay, you have to stop sharing your screen, please.
Okay.
Okay, thank you. Okay, while we wait for Steph to figure out how to do that, there is one question here. Let's see. So we have several. One is, what is the most interesting part of Bepicolombo? I think you answered that already. What is expected to learn from Bepicolombo? You also, Bepicolombo mentioned about the process of mercury formation. You gave some hints that we might have information on that, but that would also affect information about how our planet was formed, right? Or the moon, or do you expect to have any revelation coming from Bepicolombo on that side?
So if you think Mercury is like closest planet to the sun system, right? And if you want to understand why Mercury itself, how it is and why Mercury is different from the Earth, so we need to really understand how the planet itself formed and evolved, which we do not know yet. We do not know why planet got its own very high core compared to other planets. So nowadays we search more exoplanets to actually understand about our own solar system and other star system. So it is very important to understand the planets forming very close to the sun like Mercury and Venus, and see why they are very different from the Earth itself. Earth is just the third planet, but it is very different from Venus and it's very different from Mercury. And Mercury, and Mercury and Venus are the very least explored planets compared to even Mars. If you say Mars is very highly explored, and that's why we need to understand Mercury to actually understand why we happen to be and why Mercury not. Yeah, I hope that's okay.
Yeah, that's very interesting. Well, actually, there is another interesting question here. Why does it take longer for a probe to get to an inner planet like Mercury, unlike a probe that's designed to study outer planets? Is it possible for the probe to use Sun's gravity to get closer inside and later correct its course to get to Mercury?
Okay, that's a very interesting question. So if you think about it, the problem with going closer to the sun is too much of power, right? It's too much of acceleration. So if you want to, how to say, if you want to go away from the sun, you use gravity assist to actually accelerate. You accelerate your orbiter or orbiter, accelerate your mission to the outer planets. But here, when it comes to Mercury, because we're going very close to the sun, we are decelerating, because every second baby Colombo is being pulled by the sun's gravity, and we need to slow down, and we cannot do that at the last minute, because that would take a very large amount of fuel that we had to launch by ourselves. So that is not gonna happen. So that's why we use the help of Earth, Venus, and even Mercury itself to slow down our baby Colombo and bring it to its own orbit. I hope I'm right. I mean, yeah.
Yeah, well, that's a big challenge. We know about that. Another question is, what is the origin of the ice on Mercury? I think you more or less talked about that, you touched that, but Tatiana from Russia follows with, why the mission is lacking a rover? Why is Bepi Colombo not bringing a rover along?
Okay, I will answer both the questions. So ice on Mercury. So yes, these ices is not the one we talk on sulfate. These ices on the Mercury poles. In Mercury poles, we have some crater interior in which sunlight never it never got sunlight. Means it was always cold for billions of years, and that's very interesting. I mean, you have a very planet very closest to the sun. It not only have volatiles in the interior, it also has exogenic volatiles stored on its poles. So let's wait for baby Colombo to know more about these volatiles. And what was the second question again?
The rover. Why does it Bepi Colombo is not carrying a rover?
Okay, that's oh, everyone loved to have a rover, but I cannot really, I think, answer this question. But a rover, again, it's even if you, okay, imagine, even if we have all this technology, I mean, all this mass, not technology, all this mass to take the rover to the Mercury surface, we still cannot have a very proper circular orbit because of the suns. So if you think about the solar, what I learned from the engineers is that the solar panel, which is actually, in the Bepi Colombo mission, in the orbiters, in the MP it is not actually facing directly to the sun. It's actually facing in a tilted way so that it doesn't receive all the sun's radiation. So we still have to develop our own technology. So our technology currently, it is not good for Mercury and not for Venus to actually land on the surface and do stuff. So we need more missions. So let's apply another missions to take a rover to Mercury.
Great idea. So I'm afraid we have to go to the last question. So Steph, you want to roll on the YouTube one? Let's see if we can listen to that YouTube video with the question. So Steph, you want to share your screen and let's try to hear the question?
Okay, give me 1 second.
It is the first time we have a question in the format of a video. Let's see.
Okay, let's try this.
We can't hear anything. Steph, we hear very far away. Okay, no. Okay, I have the question here, so that doesn't work. I have the question here. So maybe you can stop that, Steph?
Yeah.
So this is Jane de Fatima from Moreira Branco from Brazil. And she's asking, we know about the convolution of the thermal infrared spectrum of the planet Mercury and about the METRIS instrument in which it intends to map globally the surface composition of the same one in order to study the temperature variations, besides providing a vision of thermophysical properties. But what are your expectations in completing this study after 2025? And what do you expect to achieve after this study? This information was the basis for what? They impact our life, how? Oh, that's a complicated one.
That's a good question. So okay. So as I understand from the question, so she understands why we do the deconvolution, but she wants to understand why we do this. I mean, why we have to know about the surface, why we have to know all these techniques. So like I told, like we know, so we still do not know what Mercury surface is made up of. We do not know what is the silicate. So there are hypotheses like Mercury surface has graphite and it has sulfides. There are so many clues or so many ideas, but these ideas have not yet tested. And that's what we will come to know after 2025. After 2025, we will know what Mercury surface is made up of. What is the volcanism on Mercury? Why Mercury had its volatile stored in the interior, and where it was stored, and how long it was active. And these are the questions we will know after 2025. And why this is important to the people on Earth is, so that's the bigger question, right? I mean, why solar system happen to have a Earth-like body where it can sustain life, where it actually brought life? So it is not just important to learn just about Earth. It is very important to learn how the solar system itself formed, how each body evolved, and why we are just one missing one piece for the whole clue. So we need to understand from Mercury to outer Kuiper belt and even other exoplanets to actually understand how Earth itself got its own life. So I think that's what we need on Earth.
No, very good answer. Very good answer.
Thank
So I'm afraid we are reaching over 1 hour now.
you. Oh, sorry.
From this talk, very interesting talk. Thank you very much for your contribution. I think you have several very nice and exciting discoveries ahead of you in your career. We wish you all the best, and we are all looking forward to see the results that this important mission is going to bring to us. I would like to thank our audience for joining us today. We will be back next month with another webinar. Keep tuned in our social media. We will be announcing this. So thank you very much, everyone. Thank you for the team to organize this, and see you all soon somewhere online. Thank you very much. We have all the participants saying thank you and bye-bye, and also the students that are watching this are also thanking you. So thanks everyone, and till next time.
Thank you, Europlanet. Thank you, everybody. Thanks for watching.